Donut Lab is making one of the boldest battery claims in electric mobility. Solid-state cells with high energy, very fast charging, long life, and a path into real vehicles. The question is not whether that sounds exciting. It does. The question is which parts are backed by public evidence and which parts still need proof. The viral numbers are 400 watt-hours per kilogram, about 5-minute charging, and a 100,000 cycle life claim. In plain English, that means lighter packs, shorter charge stops, and batteries that could last a very long time. The catch is that each number needs its own evidence. A good battery story is not one big number. It is a set of numbers that survive the same real-world conditions. Here is the C-rate idea without the fog. A 26 amp-hour cell can deliver or receive 26 amps at 1 C. At 11 C, the current is about 286 amps. That is a lot of current for one cell, so the fast charge result is impressive, but it also raises heat and control questions. The strongest public data point is fast charging. Public reporting says VTT tested customer-supplied cells identified with Donut Lab, and a 26 amp-hour cell reached 0 to 80% in about 4.5 minutes at 11 C. That supports the fast charge story, but it is still cell-level evidence. Why does heat matter so much? Current moving through resistance creates heat, and at high current, the heat rises quickly. Think of it like pushing a lot of water through a narrow pipe. The cell, cables, contacts, and cooling setup all matter. A fast charge that works in a lab still has to work in a pack. For normal viewers, this is the difference between a peak demo and a charge speed you could actually trust. The high-temperature tests are useful, but they are not a complete safety case. Public material describes discharge at elevated temperatures, including around 80 and 100 degrees Celsius. That is interesting because it shows stress testing. But pouch behavior and mechanical changes still need careful interpretation. The self-discharge result is another useful but narrow piece. Reporting describes a cell held for 240 hours and later giving back about 97.7% of charged capacity. Put simply, it did not appear to leak away much energy during that storage test. That does not prove everything else. Solid state means the ion path uses a solid electrolyte instead of the more common liquid electrolyte system. That can help with safety and energy density, at least in theory. But it also creates hard contact problems. The layers must stay pressed together and ions must still move easily. A simple way to picture it is a sandwich where every layer has to stay flat, clean, and touching. The failure modes are not mystical. The solid layer can crack. The contact between layers can get worse. Internal resistance can rise, which means more heat and less efficiency. Lithium can behave badly if conditions are wrong. So the question is not just can it work once, but can it keep working? That repeatability is what separates a cool lab result from a battery you would put under a seat. A great cell does not automatically make a great pack. A pack adds bus bars, wiring, cooling plates, compression hardware, sensors, safety electronics, and a protective box. All of that adds weight. So a cell energy density claim is exciting, but the pack level number is what a vehicle actually feels. The battery management system, or BMS, is the referee. It watches voltage, current, temperature, and cell balance. If one group of cells gets too hot or ages faster, the system must reduce power. That is why a 4-minute lab charge and a 4-minute vehicle charge are not automatically the same thing. On safety, solid state may reduce some risks, especially if there is less flammable liquid inside. But less risk is not the same as no risk. Real proof would include crush tests, puncture tests, overcharge tests, short-circuit tests, and pack-level propagation tests to see whether one failure spreads. Damage tolerance also needs plain language. A cell surviving a harsh test is good, but we need to know what happened after. Did capacity drop? Did the pouch swell? Did resistance rise? Could it still be safe in a product? Survived is a start. Qualified is a much higher bar. In consumer terms, the question is whether the battery is still useful and predictable after the stress. The 100,000 cycle claim needs context. A cycle means charging and discharging, but the conditions matter. Was it shallow cycling or full cycling? Was it hot or cool? Fast or slow? One cell or many cells? Without those details, the number is interesting, not settled. Think of it like tire mileage. The number changes depending on how and where you drive. Manufacturing is where many battery breakthroughs get slowed down. A lab cell can be made carefully by experts. A factory has to make thousands or millions with the same quality. Tiny defects, moisture, pressure variation, and layer thickness can all change performance. Yield and cost matter as much as chemistry. When a company says production ready, I want simple evidence. How many cells were made, how consistent they were, how many failed, and what the cost path looks like. That kind of data is not as flashy as a spec sheet, but it tells us whether the technology can scale. If only a few hand-built cells work, that is progress, but it is not the same as a factory-ready battery. The motorcycle angle is why the story is exciting. Motorcycles do not have much room for batteries, and weight matters a lot. A lighter, faster charging battery could change range, handling, and packaging. That is the dream version of this technology if the cell results translate into real packs. Road validation connects the lab to the rider. The pack needs repeated fast charges, cold starts, hot weather, vibration, hard acceleration, and normal aging. Then you check capacity again. If the numbers still look good after that, the story becomes much stronger for real-world use. That is when the claim starts to feel less like a lab chart and more like a product. The evidence matrix is mixed in a useful way. Fast charge evidence is the strongest public area. Storage behavior has a helpful data point. High temperature behavior is interesting but needs caveats. Chemistry, pack energy density, long cycle life, safety at pack level, production yield, and cost still need clearer public proof. The hype makes sense because the upside is real. If Donut Lab can deliver high energy, fast charging, safety, and long life together, it could change pack design. The important word is if. We can be excited about the possibility while still asking for the full measurement package. That is not being negative. It is how you protect yourself from overreading early data. A strong proof package would be easy to understand. Show independent chemistry checks. Show measured mass, dimensions, voltage, and energy. Show cycle life with conditions. Show safety reports. Show pack-level road data. Show manufacturing yield. That would move the story from promising to much harder to argue with. What should people watch next? Not another render and not just another headline. Watch for repeated third-party tests, multiple sample cells, pack-level fast charging, clear cycle plots, and manufacturing data. Sample count matters because one excellent cell does not prove a production platform. The more boring the data looks, the more useful it usually is. The fair verdict is promising, but incomplete. The public fast charge data is strong enough to pay attention to. The broader breakthrough claim still needs more public proof. That is not a takedown. It is just the normal difference between a great cell data point and a finished vehicle battery. The exciting part is real, but the checklist is not finished. So keep the excitement and keep the labels. Fast charging has meaningful support. Thermal and storage results are useful but narrow. Energy density, long life, low cost, and pack readiness still need the full dataset. That is the balanced version. Exciting technology, real questions, and a clear path to proof.